Welcome everyone. In today's webinar about formation damage, which will be talking about causes, prevention, and mitigations that will be, come through. So actually, I'm thrilled to have such a diverse group. I can see the participants. They are variant. Some are professionals, and some they're fresh graduates. So I choose this topic. Actually, it's the formation damage is a critical topic that affects us all, and obviously understanding it is a key to maximizing the well productivity and ensuring the long-term success of our operations. So during this webinar, we'll be talking about a couple of topics. Starting with the introduction, we'll see what is the formation damage, what are the main causes of formation damage, the things that contribute to formation damage. And then we will see how can we diagnose any formation damage that could be occurred during the well life. And then we will go through how to prevent the formation damage before it's happening. And what if the formation damage, or once the formation damage happens, how can we mitigate or reduce or limit the bad effect of formation damages? And then finally, we'll see a summary, and I collected some points for you to take it. This is going to be a brief presentation. It's not a very detailed, but I wanted to go through the most important and the common features that you may need to know about formation damage. And finally, of course, you'll see the question and answer section. So formation damage is actually, you can see the picture on the right. I meant to put this picture. Actually, you can see how sad this guy looking for is actually pretty much represents our faces when we have or when we come across formation damage case. So formation damage refers to the impairment of the reservoir ability to produce hydrocarbons due to the physical or sometimes chemical alterations in the rock and in the fluids, often resulting from various operations of resulting from drilling, completion, or even production activities. So preventing formation damage is a very a key element in our operations. So when we talk about formation damage, we are addressing a significant challenge in the oil and gas industry. For example, there Mr. Emefel and his group in 1988, he describes the formation damage as an expensive headache for the industry. So this description highlights not only the technical complications associated with the formation damage, but also the substantial economic as well. So the costs related to mitigating formation damage, coupled with the potential loss of productivity, and make it, as a serious, concern of the operations. And as well, Mr. Farouk emphasized that the operational and economical drawbacks of the formation damage, which could be defining as the undesirable operational and economic problem. So this was his definition to the formation damage. It's of course it's undesirable operational thing. So the perspective underlines the direct impact of formation damage on the reduction of the oil and gas industry. And this decrease in the reservoir permeability caused by the formation damage can lead to significant losses in the output, making it a critical issue for maintaining what we call the profitability and the efficiency of the oil industry. So now we are talking about a serious issue that is threatening the oil industry in general due to the continuous decline that we are facing in all global fields in the world. So if we would like to define somehow the formation damage, formation damage poses a significant challenge. So now we have a challenge in oil and gas industry leading to substantial decrease in the well productivity, and this as a result resulting in billions of dollars are being lost, in the revenue globally by year. So the productivity loss translates into a major financial impact, and this is affecting the profitability of companies in the world. So can you imagine how much serious this issue and needs to be, well addressed? So addressing the formation damage is therefore crucial, and it's not only for optimizing well performance, but also for mitigating the extensive economic losses that the industry, annually faces. So if someone asks you, what is the formation damage? By definition, the formation damage refers to any physical or chemical alteration of the reservoir rock and its surrounding fluids that impairs the ability of the reservoir to produce hydrocarbon in a very efficient way. So this physical alteration results in the reduction of the permeability, and also sometimes the reduction in the porosity, and sometimes in both, in porosity and permeability, and affecting overall the productivity of the well. So formation damage can occur at various stages, as I have mentioned, either including the drilling, completion, and production. So understanding the context helps you to identify where and why the damage might occur, allowing for better management and better mitigation strategies that you may propose for the formation damage. So let's go a little bit deep and see what are the main impacts of formation damage on the production and reservoir performance. So the first thing comes to your mind is the reduced permeability. Formation damage often leads to decrease in the permeability of the rock. This means that the flow of hydrocarbons throughout the reservoir is restricted and reducing the well's production rate. Another thing is decreasing porosity. So the damage of the formation can also affect the rock's porosity, which where the measurement of the void spaces. So we're talking about the volumes of our hydrocarbons is being reduced. So the reduced porosity means there is less space available for oil and gas storage, and this reduction can be caused by several means, as we will see in the upcoming slides. But for example, the drilling fluids, or for example, the dissolutions of soluble minerals, all these stuff that may reduce the porosity. Other thing is the increasing in the flow resistance. So as we have the formation damage, this increases the resistance to flow within the reservoir. This can lead to higher pressure drop, meaning that we need more energy is needed to extract the same amount of hydrocarbon. So once we have formation damage, we need to apply more energy. We need to create more pressure difference between the reservoir and the wellbore condition to extract the same amount of hydrocarbon, which will lead to another problems. So increased flow resistance can also result in what we call uneven reservoir depletion. So the reservoir is not depleting equally, and this is a very, very serious issue. And what's happening, it affects it's really hard, it's really difficult um, let's say, monitor and manage your reservoir, because you have no control about the fluid movement throughout the reservoir. So this is affecting, in other words, affecting the overall efficiency of our hydrocarbon extractions. The last, impact, and I see it's a very serious one, which is impact on reservoir management. So formation damage impacts the reservoir management strategies by limiting the effectiveness of any, for example, enhanced oil recovery techniques that you may apply. For example, let's say techniques like water flooding or gas injection may be less effective if the formation damage, prevents proper fluid injection or displacement. So we're not performing the displacement in the proper way, as a long-term reservoir performance is, compromised, as damage can lead to uneven production and reduce the recovery factors, as I've just mentioned. So this is actually the definition of formation damage and its impact overall. So now let's see what are the main causes for formation damage. Formation damage can be broadly categorized into two major causes, if I may say, in damage. The first one, what we call induced damage, and the other one is a natural formation damage. So let's start with the first one, which is the induced formation damage. These kind of damages are, caused by human activities and caused by operational practices. So basically, this sort of damage is caused by us. We are responsible for having this sort of damage. And talking about the induced damage, I will start definitely with the drilling-related causes. The first thing in the drilling-related causes is the over-balanced drilling. Of course, our brothers in drilling departments, they want to ensure that the drilling process will go smooth without any blowout, without any, let's say, technical issue while drilling. But at the same time, we look into the reservoir itself and we see what are the impacts of what are the consequences of drilling over balanced drilling. So drilling with a hydrostatic pressure that exceeds the formation pressure can cause the fluid invasion into the formation, leading to the clogged pore spaces and eventually reducing the permeability. And here, when I say exceeds, I'm saying it up to the limit. For example, it's been said that if the drilling or hydrostatic pressure exceeds the formation pressure by 200 psi, we are more or less in a safe side. But as this difference gets bigger, so we are, expecting some sort of damage will be, we're expecting more invasion will happen, and we're expecting more less or reduction permeability will occur. The other thing is invasion of drilling fluids. So the penetration of drilling fluids into the reservoir rock leads to formation damage by introducing fine particles and chemicals that block the pore spaces and eventually alter the rock properties. So I would like to tell you about a case that I've been through. There was a field that is being drilled with certain mud pressure. So the hydrostatic pressure, at certain mud pressure, the hydrostatic pressure that was considered in the early stages of the field. But after 10 years of production, the reservoir pressure reduced drastically. And however, unfortunately, the same hydrostatic pressure was being applied even after the depletion. So it has been noticed that almost all of the wells that were drilled after the depletion, they have never produced. So basically, this was a very good lesson that was learned from that companies by actually trying to find a way to change their mud properties, mud pressure, the drilling operations itself to accommodate the reduction in the reservoir pressure. So obviously, we need to pay attention to the reservoir pressure. Otherwise, we will not be able to produce. And by the way, there was a very successful stimulation job has been performed to that field, and the well started to producing again after stimulating it, as we will see. Let's continue our induced formation damage. The other thing is the completion related causes. So the first one is what we call a poorly designed completion. Sometimes we have inadequate selection, like inadequate installation of well components, and this actually may result in insufficient flow paths and increase the risk of formation damage due to poor communication between the reservoir and the well bore. So as may probably you know this, sometimes not perforating the whole reservoir, the whole oil zone, this may lead to what we call the spherical flow that could be detected while analyzing the pressure transit analysis. And this is increases or inducing another what we call skin due to the partial penetration of the reservoir. So inadequate installation or selection of our completions may raise sort of damage. The other thing is perforation. Probably some of you might be surprised that perforation, is it like a potential source of damage? The answer is yes, potential. It's a potential source of damage because perforating is always a cause of additional damage in formation rocks, whether it's performed over balance or even under balance. It always compacts the rock around the perforations and reduces a zone with average thickness around 1 centimeter, which is half inch, with the permeability reduction to 80% due to the compaction that occurs after performing the perforation. So the permeability reduces just around the perforation by it reaches up to 80%, which is a drastic decrease of permeability. So another issue that may arise while performing perforation is perforating over balance. Always forces deformation and gun debris into the perforation wells, and eventually it will decrease the permeability near the perforations. So this, could, if the perforations are not clean, so that's why we another solution has been implemented in the underbalance to perform perforation and clean up the perforations, avoiding pushing all the debris and any debris into the formation. Instead of that, by performing underbalancing pressure will reduce this sort of damage. And then another thing, that if there is insufficient penetration, so if the perforations were not sufficiently penetrated and bypassing the drilling damage, so the perforation will not help us to start production. So choosing or selecting the proper way of your completion and of your perforation, the number of shots and the type of perforation, the thickness and everything, all these informations are very critical and may increase or raise some sort of damage. Another induced formation damage, which is while production. I mean, it's a production related causes. Um, when it comes to production, yes, there are some damages that are being raised while producing the well. The first one is the excessive drawdown. So a rapid reduction in the reservoir pressure due to production actually causes a reservoir rock to collapse, and also it may alter the geomechanics of your rock properties, and eventually it changes the reservoir rock property as well. So I'm not talking about the fine migration that's going to be in the other part of the natural formation damage, but also could be as a result of high drawdown that may be applied to our well, that will trigger the fine to migrate throughout the reservoir, blocking the pore throats. Another thing in the production-related causes, which is the acidizing and hydraulic fracturing impacts. So yes, they are supposed to stimulate our well instead of damaging it, but there is some limitations and there are some risks to have some sort of damage as a result of acidizing. So injection of acid to dissolve formation rock and improve permeability. This could be a potential for over acidizing to damage the rock structures and reduce the long-term productivity if the acidizing will not very well optimized. And another thing, the hydraulic fractures. If we apply like a high pressure fluid injection to create fractures into the reservoir, this risks to include uncontrolled fracture propagation and throughout the reservoir, and it could raise formation damage due to proban impediment, for example. So these are the most common formation damage that is because of our operations or our human factors. Now let's move on to the other sort of or cause of damage, which is the natural formation damage. So these are the damages that are arising from natural process and conditions. So mostly we have no control about, in most of the cases, not all the cases, we have no control about these causes of damage, but we can mitigate these sort of damage as well. Starting with the natural process, this is occurred over the depositional process of the rock itself. So the first one is the formation compaction. Of course, as you know, that the compression of the reservoir rock over time due to the weight and overlying sediments can reduce porosity and permeability, and therefore affecting the hydrocarbon flow. The other thing is after the deposition happens, the what we call the diagenesis process that alter the reservoir quality. For example, the natural minerals that deposits that binds the rock grains together and leads to reduced porosity and permeability, leading to less hydrocarbon production. So as I told you, these are factors that are not actually well controlled. The other thing is the geological factors. For example, the presence of fines and clays. This is a very common issue, which is the natural occurrence of fine particles and clay within the reservoir rock can potentially lead to pore throat blockage and reduced permeability. The reservoir heterogeneity as well, the variations in the rock properties and fluid distribution within the reservoir actually creates uneven flow paths and can complicate the extraction of hydrocarbons. And finally, some natural fluid interactions that may occur, for example, when we have a water influx from aquifer to the reservoir, the entry of water into the reservoir from surrounding formations can alter the pressure, the reservoir pressure, and lead to a formation damage. Some interactions like chemical reactions, for example, natural chemical interactions between formation fluids and rock minerals may lead to dissolution, mineral dissolution actually, or precipitation, and if this actually affecting the reservoir properties. So this subdivision helps to clarify how different factors contribute to formation damage and provides a more organized view of both a human induced and natural causes. So let's talk a little bit more about the clays and fine migration because this is a very important one, especially that's related to the production. So clays are classified based on the crystalline structure. And these structure differences, determine the amount of surface area exposed to the reservoir fluids. So there are some clays will change in volume. I mean, they will swell depending on the salinity of the fluids they are exposed to. So this is the first type, which is the swelling clays. The decrease in the formation permeability due to this, swelling effect is dependent on several parameters like clay type, amount, and the location with respect to the flowing fluids. So this is like the bad effect of the swelling clay. So what is the most common clay mineral that it easily gets well, which is called smectite or smectite mixtures? These are the most common swelling clays that you may ever know, and these clays can show an increase in volume up to 600%. So can you imagine that a very small size of this mineral maybe get bigger or get swell when are they exposed to water up to 600%. So if this is a very, very serious issue. Sometimes we see that after producing water, there is a drastic decrease in the production. And this is actually one of the major reasons. So if the swelling clays on the larger or major pore throats of the formation, so the permeability reduction will be much more severe than if they are occupying the small pore throats. So when there is a water paste, filtrates from whatever you have, drilling, completion, workover, that invades the porosity of the reservoir, they can distribute the when the water distributes into the reservoir, this can disturb the equilibrium between the clays and the formation waters. This normally due to the change in salinity that is creates or that is creates the imbalances in the forces between the clays. So smectite clays can swell and drastically reduce the permeability. This disturbance that was created of native clays is the most common and probably the most important cause of damage. Moving to the other type, which are the migratory clays or fine migrations. Known as migratory clays are prone to movement within the reservoir due to their unique properties. And this includes what we call illite. So illite has the ability to move throughout the reservoir when influenced by the fluid flow or the changes in the reservoir conditions. This migration actually can affect the distribution of illite particles within the formation and contributes to the blockage and permeability issues. Unfortunately, that illite migration can lead to the transport of fine particles throughout the reservoir. So you can see that these pictures that shows how these particles of illite moves throughout the pore throat, and they are blocking the small pore throat in our reservoir. Once they get stuck in smaller pore throats, or they accumulate in very small pore throats, and eventually they're reducing permeability. So as you can see here, that on the upper left part of this slide, that illites, it's like has a lattice structure. This include potassium ions that are situated between the silicate sheets. As you see here, there are some silicate sheets, and they are separated by potassium, and this potassium is actually controls the stability of the clay and ensures minimum volumetric changes. So that's why basically for illite, it hardly gets swelling, or hardly gets bigger, but it moves throughout the pore throat. So once the water block occurs, when we are injecting or changing the fluid chemistry, that cause illite structures to dislodge or deattach and migrates as a result in a change in the salinity in water flooding, for example, and leading to a blockage in the small pore throats. Another clay mineral, which is called kaolinite. So kaolinite particles can become, mobilized and move within the reservoir, potentially leading to formation damage. Regarding the kaolinite particles are relatively large compared to the other clay minerals. So these large particles have more substantial impact on the pore spaces. So when you have kaolinite in your reservoir, this is not a good news that you may have. And when these relatively large particles migrate throughout the reservoir, they can block the pore spaces and reduce the effective flow area of the hydrocarbons. So movement of kaolinite is a really bad news for our reservoir, for the reservoir engineers, and this is because leading to decreased permeability and decreasing the production rates. There are some other types like chloride. Chloride is categorized like a group of clay minerals with complex structures, often exhibiting the low swelling properties, same as illite and kaolinite. But unfortunately, they can migrate throughout the reservoir, particularly in when we have changes in the fluid chemistry. So changing the fluid chemistry, as you may have noticed, it has a very bad effect even on the fine migration. So the movement of chloride can contribute to the obstruction of the pore spaces as well. And there are some other migratory minerals like feldspar and fine silicate. Like all these particles can migrate and deposit in the pore throats, leading to a reduced flow capacity and creating a formation damage. Of course, when we are talking about formation damage, we cannot forget the scale buildup that may occur while even while production or while performing any stimulation operation. So saturated brines may form precipitations when minerals equilibrium concentrations are exceeded due to many factors. So when the water brines get into the reservoir, and this causes several damages as a result of three main parameters. The first thing is the increased mineral concentrations. We have more mineral concentrations in our reservoir as more, water is coming through. I mean, I'm not talking about formation water, I'm talking about external water. The change in the temperature, the change in the pressure, the change in the pH, all these different type of water is being injected into the reservoir creates sort of interactions or chemical reactions or that creates to deposit of a scale or building up a scale either in the wellbore or in the reservoir. And of course, when it happens in the wellbore, it's more or less we can manage it. But if it happens inside the reservoir, it's going to be a serious issue. The other parameter, which is mixing incompatible waters. So not only different properties, different salinity, different pressure, different pH, but also sometimes it's even worse. We are mixing incompatible water and exposing it to our reservoir and our wellbore. So injection wells, this is may result in, for example, it may result in a scale buildup. And for example, you have sodium sulfate, and with a barium chloride creates a participate called barium sulfate. And this Mr. Barium sulfate is insoluble in HCl, and it's really hard to dissolve, if it's not possible to dissolve this kind of participate. So injecting water in our reservoir, either during drilling or any completion, or sometimes even the workover during killing the well process, might create these kind of scales. So in carbonate, as the pressure decreases, there is CO2. CO2 is actually evolves, then the pH increases. So as a result, there is CaCO3, calcium carbonate, are dropping out. But fortunately, that this solution, out of solution, it could be dissolved in HCl later on. So that's why HCl is a good solution for carbonate rock, carbonates, and in general, as we will see in the upcoming slides. So now up until now we were talking about the main causes of damage. Now let's see how can we diagnose if we have a formation damage or not. So diagnosing the formation damage is a critical step in identifying the causes of reduced well performance and implementing effective remediation strategies. So this is step number one in our remediation and our mitigation process. So if we have accurate diagnosis, this involves a combination of direct and indirect methods which help determine the extent and the location and the natural formation damage. Here are the most common approaches to diagnosing the formation damage. Of course, I will start with the well testing and the production data analysis. What I mean by production data analysis is actually the decline curve analysis. This method involves, analyzing the production decline curves over the time to identify abnormalities that may indicate the formation damage. Like we normally have a stable decline or a stable, let's say, liquid rate, and sometimes we might have a sudden drop in the production rates. This could be an indicator to, or could be a signal to have a damage. So this is our the most famous technique. The other technique, which is a very comprehensive technique, which is the pressure transit analysis, or what we call the PTA. Pressure transit analysis actually involves analyzing the pressure buildup or drawdown tests to evaluate the reservoir properties and detect the formation damage. A reduction in permeability or increase in the skin factor, which is an indication of formation damage, can be identified throughout the analysis. So the skin is actually, for those who are fresh graduates, skin factor is a dimensionless parameters that quantifies the extent of formation damage or enhancement if around the well pore, if we have negative or positive skin. So a positive skin factor indicates damage, which is reduced the permeability near the well pore, while negative skin factor suggests stimulation or enhanced permeability around the well pore. So during the pressure transit analysis, the skin factors calculated by analyzing the pressure differences between the actual well performance and the ideal well performance or undamaged reservoir conditions. So this is basically the main concept of the skin factors. And eventually the PTA analysis allows you to quantify the degree of damage and helping operators understand how much the damage is affecting the well productivity. And by analyzing the pressure drawdown and the pressure buildup, the PTA can estimate the effective permeability of the reservoir. So if the permeability is sharply or significantly lower than the expected, or lower than the previous permeability, if there are more than one, it could be an indication for a formation damage. There's another indicator here, which is the most important indicator, which is the productivity index. Productivity index is basically a measure of well's ability to produce hydrocarbons, and it's directly related to the reservoir permeability and the skin factor. So it actually represents these two parameters that eventually they are describing the formation damage. So formation damage typically reduces the productivity index, which can be observed throughout the PTA. And a declining in productivity index over time, especially when compared to the initial conditions, is a strong indicator of a progressive formation damage. So these are our first tool, which is analyzing the well test and the production data that we have to identify whether we have formation damage or not. And there are some other tools, which is the core analysis. In the core analysis, you can do some core sampling or some laboratory tests that are, specialized in identifying, to simulate the reservoir conditions and help to assess the extent of formation damage caused by the fluid interactions. There are some courses that help us to identify the clay minerals. So one of the things that you may need to do as a reservoir engineer, go and ask your partner of geologist that works with you, and ask for the thin section petrography, for example. The other method to have the clay minerals is the X-ray diffraction, and there's another mean. I think it's called the scanning electronic SEM. I think microscopy. So yeah, these are the ways that you can know what are the clay minerals that you have, and then identifying the clay minerals, the cementation materials, the percentage of carbonates, all these informations that could be identified by these methods. So therefore, they may help you understand the formation damage. And another method, which is the fluid sampling and analysis. So just by analyzing the composition of the produced fluids, oil, water, and gas, what you have, and this can provide insights into formation damage. And if you have any fines or clays are being produced with the produced fluids or high water cuts, this may suggest a formation damage. The other thing is changes in salinity. This also could be an indicator for formation damage. For example, the change that happens in the ion concentration in the water formation can indicate to chemical interactions. These chemical interactions are being contributing to causing a damage. Some sort of interactions like the one that I have mentioned earlier, which is the clay swelling and the scaling. I'm sorry, I still have the last one, which is there are some specialized laboratories that performing some sort of, for example, sand production testing. So lab tests that can simulate reservoir conditions to assess the potential for sand production, which can be both a cause and a consequence of a formation damage. So high sand production rates, this indicate the destabilization of the formation due to the damage. So once we have the formation, the sand production, that it gives us a hint there is some fine is being migrated, not only a sand but also some other clay minerals that are being moving throughout the pore spaces or pore throats. This help us understand if there is some sort of this kind of damage or not. Also, there are some scale and corrosion testing. Some lab tests, they can evaluate the scaling and corrosion potential of the reservoir fluids, which are common causes for formation damage. So I've just have mentioned the most common methods or means to diagnose the formation damage. Of course, diagnosing formation damage requires a comprehensive approach that combines multiple diagnostic tools and techniques by analyzing web performance data, core samples, logging results, fluid compositions, and downhole monitoring. There are some many things that you can do to diagnose the formation damage, and usually operators can identify the type and location and the severity of formation damage by these methods. Obviously, early and accurate diagnosis is crucial for selecting appropriate remediation strategies and minimizing the impact on well productivity and reservoir performance. So we do not wait till too late to do the mitigation process. Now we have already now finished talking about the how to diagnose formation damage. Now, before this damage happens, we don't want to wait till this damage to happen. We are thinking about the ways to prevent the strategies. Sorry, I'm just receiving an important message right now. Okay, so this is the preventing strategies. Talking about there is a crucial or preventing the formation damage is crucial for maintaining the reservoir productivity and extending the life of the well. So now we'll be talking about the strategies for minimizing the risk of formation damage throughout the optimized drilling practices and effective completion design and careful production monitoring. So the first one is the optimizing drilling practices, which is start with the proper mud selection. The choice of drilling mud plays, a vital role of in preventing the formation damage. Because the mud should be in the first place should be compatible with the reservoir rock and the fluid properties. So it's actually the solution is to use low filtrate methods to reduce the invasion of the drilling fluids into the formation, which can block pore spaces and reduce permeability. For the clay stabilization, sometimes you may select muds that prevent clay swelling and dispersion. For example, potassium paste or polymer paste muds, they can help stabilize clays like illite and kaolinite, so they so they will not swell and reduce the risk of fine migration. Other mitigation or prevention, prevention strategies is to use drilling additives, like they can be used to mitigate potential formation damage during drilling process. For example, use inhibitors that prevent chemical reactions between the drilling fluids and formation, such as clay stabilizers and scale inhibitors. Other strategy that you could do while drilling activities is the fluid loss control. You can have some kind of additives that control the fluid losses and prevent the invasion of harmful fluids into the formation. So this is how to prevent somehow the formation damage while drilling. Now we move on to the other one, which is having effective completion design. Obviously, selecting the appropriate completion techniques. I mean, the design of the well completion must minimize the potential for formation damage while maximizing the hydrocarbon recovery. For example, choosing between open hole versus cased hole completion. Choosing between open hole and cased hole completions based on the formation characteristics. This is what controls the decision here. So for open hole completions, they can the risk for damaging the formation, because there will not be perforation nor cementing nor casing, while case hole completions offer better control over the sand production and the fluid management. So these kind of strategies that helps you identify the best completion that you may do. The other thing is sometimes using formation isolation. We don't need to expose all our formation to the killing fluid, for example. We can use packers or liners and other isolation tools to predict the sensitive zones, if any, from being exposed to potentially damaging fluids. Other techniques, there are gravel packing and the use of screening this, their objective is actually preventing the migration of formation fines and sand production, which can cause severe damage to the well and formation itself. So these are, the methods to prevent the formation damage. Moving to the last, but not the least, way to prevent formation damage is monitoring and adjusting production. So after, once the well is being produced, of course, monitoring the production plays an important role. For example, we have continuous monitoring of the reservoir conditions for early detection of the formation damage. This is very important to prevent the formation damage, because it could be easily detected in the early stages. And and the strategies is actually by performing like regular monitoring of reservoir pressure, making sure that the reservoir pressure in the good range, and the production rates to detect any sudden changes in that might occur or might indicate the formation damage. By actually using periodic logging and imaging tool to assess the condition of the formation and identify early signs of damage, such as changes in the permeability and the presence of fines, as I've mentioned earlier. So monitoring, it can help you to detect any formation damage in early stages, and then after that it helps you to do the proper actions. Controlled production rates. Of course, proper management of production rates is a key to minimizing the formation damage by, particularly the sensitive formations. So, as I have mentioned earlier, applying high drawdown pressures can lead to fine migrations and sand production, and increased water cut, all of which can cause formation damage. So gradually increasing of production rates can help prevent these issues, instead of applying very high drawdown. So adjusting the production rates based on the reservoir conditions and the well performance data to maintain a balance between maximizing recovery and minimizing damage. So by implementing these prevention strategies, like optimizing drilling practices, designing the effective completions, and carefully monitoring and adjusting the production, of course, you can significantly reduce the risk of formation damage, and thereby maintaining reservoir productivity and ensuring the long-term success of the well. I think now I've been presenting for an hour now. Hopefully, it should not take probably 15 minutes, and then I will open the door for a discussion. Here we came to the last stage, which is after confirming and diagnosing our case, and we have the formation damage. Now we would like to mitigate, we would like to overcome this formation damage. So I wanted to make it simple but effective at the same time. Here we have the mitigation techniques for the formation damage. So Mitigation strategies for the formation damage can vary significantly. Depends on whether the reservoir rock is, is a sandstone or a carbonate. And also it depends on how much severe your formation damage is. So all these should be taken in considerations to provide or propose the proper mitigation techniques. So here in this slide, I'll provide a detailed overview of acidizing treatments and also yeah, acidizing includes three types of acidizings that you may need in both in sandstone and and carbonate formations. So I started with sorry. I started with acid wash here. If it's there are three types of acidizing. Um, the three types, the difference is the injection pressure. So as a general rule of thumb, for acid wash, we inject acid below reservoir pressure, so it does not go deep into the reservoir. For matrix acidizing, we inject the acid above reservoir pressure and below fracture pressure, which means it goes inside into the reservoir. And then we have acid frac, which being injected above the fracture pressure, so it goes even deeper into the reservoir. So let's start with the acid wash. Acid wash is a common technique used to clean up the well pour surfaces and equipments. So we remove the scale and you remove debris if you have debris in the well pour, and prepare the formation for further treatments, such as matrix acidizing or hydraulic fracturing. So this is a very common techniques are being used to clean up, just for cleaning up purposes, because we're talking about the well pour scale. The primary mechanism involves the reaction of acid with a scale, acid with a rust or any other deposits that you may have accumulated, in the well bore. And the main purpose of acid wash is primarily to, as I said, to clean up and removing the scale. And this sometimes all what you need is just you need to clean up the deposit and the scale around the well pour, and then all the damage as being gone. So it appears that the well pour and the near well pour formation, of course, as I said, the acid wash does not go deep into the doesn't go into the reservoir. Moving to the main types of acid that are being used as acid wash, the most commonly used is the hydrochloric acid. This is very common in acid wash. HCl is very effective at dissolving carbonate scales like calcium carbonate and iron-based deposits. These are very dissolvable and easy to be vanished when it's interacting with the HCl. There are some other acids like acetic acid and formic acid. These are sometimes used as alternatives to the HCl. Exactly when a less aggressive acid is needed, or when the formation is really sensitive to strong acid, we use this kind of organic acid. So sometimes we have mixtures like of HCl with other acids or additives are used to target specific types of deposits and to enhance the reaction. So now, what are the considerations that we need to consider while performing the acid wash? The first one is the compatibility with the formation. So that's why it's better to take a sample of the scale or whatever exists, and we perform a compatibility test. So we need to take care to ensure that the acid does not react adversely with the formation itself, especially in a sensitive or heterogeneous formation. The other considerations we need to take is the acid strength and the acid volume. So the concentration and the volume of acid, are used must be carefully controlled to avoid over acidizing. This can lead to excessive corrosion or a damage into the formation. Another limitation, if I may say, for acid wash needs to be considered is higher temperatures can accelerate the acid reactions, which could be like beneficial to it could be like depending on the specific situation. For example, the temperature control or the use of acid retarders may be necessarily, because the higher the temperature, the accelerate or the fastest the reactions. And sometimes when it reacts so fast, it does not react with the whole scale that you have, and eventually will not be much effective. The other thing is corrosion control. Nowadays, corrosion inhibitors are often added to the acid wash solutions, to protect the well pour tube and the production string, the downhole equipment from the acid, and to prevent any corrosion or to be harm to our production string. So finally, for the acid wash, the main applications are to remove the scale, such as calcium carbonate, iron oxides, and other deposits from the well pour, and it's a good option for well pour clean out before more aggressive stimulation treatments. Sometimes you might have debris, and this debris go deep inside into the reservoir, so it's better to clean up the well by using HCl, as I have mentioned, and also its application to for equipment maintenance. Acid wash is also used as part of regular maintenance to keep downhole equipment such as screens and perforations free from blockage, and they have a very good access to the reservoir. So the acid wash is crucial process in the well pour maintenance and preparation, primarily aimed to cleaning of the well pour and the equipment from the scale or from other deposits. And by dissolving these obstructions, acid washing ensures that the subsequent treatments like matrix acidizing or hydraulic fracturing can be performed more effectively, leading to improved well productivity and longevity. So moving to matrix acidizing. Matrix acidizing, as I have mentioned, which is applying or injecting the acid with a pressure above the reservoir pressure, but lower than the fracture pressure. So basically is a well stimulation technique used to improve the permeability of the reservoir rock by dissolving formation minerals near the well bore. I would like to emphasize about that is near the well bore. The process differs, in sandstone and carbonate formations due to the difference in mineralogical compositions of these rocks. Starting with the sandstone formations, as you know that the composition of the mineral composition of sandstone primarily composed of quartz, which is silica, grains with varying amount of feldspar and clay minerals like kaolinite, illite, and chlorite. So these are the composition, the mineral composition of the sandstone. And also, as I said, the clay minerals can contribute to formation damage either by swelling or fine migrating and blocking the pore throats. So it has been said that in sandstone, it's not a well simulation. It's more of a damage removal because the acid does not actually react, as I will talk a little bit later. The acid does not react with the quartz grains, does not react with the composition, rock composition itself. So if there is a damage, either clay minerals or the minerals due to drilling or completion, it will remove that. It will help us to remove this damage. But if there is no damage, if there is no clay minerals, so in that case, it will not, add any solutions. So that's why it has been said that a sandstone is a damage removal. Matrix acidizing in sandstone is only a damage removal rather than a well stimulation. So what are the types of acid are being used in sandstone? Uh, the first one is hydrofluoric acid. This is the most critical acid in sandstone acidizing, used because of its ability to dissolve silica and silica-based minerals and clays. So the presence of HF, this targeting the clay minerals and all the silica-based minerals. But we don't use hydrofluoric alone. We use HCl. And the HCl we use it normally as a pre-flush. This pre-flush is actually being used to remove any carbonates. So we inject HCl at first to remove any carbonates and other acid soluble minerals that could react prematurely with the hydrofluoric acid. So the acid is being used, the mud acid, HCl plus HF. Of course, we don't want the hydrofluoric acid to see or interact with carbonates. So that's why we are sending HCl at first to the as a pre-flush to the formation to interact or react with all the carbonates, and then we inject the mud acid to dissolve the silica-based minerals and clay minerals. So the process of matrix acidizing, I will talk it briefly, which is we have a pre-flush, which we inject HCl, and the HCl dissolves any carbonate minerals in the sandstone, cleaning up the way for the hydrofluoric acid to react more effectively with the silica minerals. And then we have the main acid treatment, which is the hydrofluoric acid, because hydrofluoric acid reacts with the quartz and other silicate minerals, this dissolving them and create more pore spaces, which enhances the permeability. Also, the hydrofluoric acid HF, reacts with the illite and chloride, where HF dissolves the aluminum and silica components of these clay minerals. But here I would like to, before going to the carbonate, I would like to highlight what are the main challenges that we have. The first challenge that we have in matrix acidizing when it comes to sandstone is secondary precipitations. So we need to take care, to manage the reaction by, products that can precipitate and cause a new blockages. So we might introduce a new sort of damage after injecting matrix acidizing in sandstone. So proper acid formulation and treatments design are crucial in sandstone to avoid precipitation of secondary reactions. The other thing, the other challenge is the clay sensitivity. Some clays can swell or shift, when exposed to acid. So potentially causing additional damage if not, properly managed. So we need to understand exactly what do we have as a cementation. We need to understand what are the clay minerals, the percentage of carbonate. All these information are important in the recipe of our design of matrix acidizing. Now we move on to carbonate. When it comes to carbonate, you can relax a little bit more because it's not, I mean, you don't need to, it's not the same situation as sandstone because basically because of the composition of the carbonate itself. Because carbonate formations, consist mainly of calcite, which is calcium carbonates, and dolomite, which is calcium magnesium carbonate. So carbonate rocks actually have, more homogeneous minerals composition compared to the sandstones, and making acid reactions, more predictable. So the main types of the acid is being used in carbonate is, as you all may know, is the hydrochloric acid. HCl is the most common acid used. There are some other acids like organic acid, for example, acetic acid and formic acid came into because they are less corrosive than HCl, as I have mentioned. So their primary benefit is high temperature applications. Formic acid is more, strongly reacting than acetic acid, and it's closer to the hydrochloric acid in strength, but still weaker comparing to the HCl. Therefore, formic acid is not often used alone. Most of the time is not being used alone, even though it could be. So when it's necessary to replace the HCl completely with a weaker acid, I think acetic acid is the common and the most logical choice. So for the chemical reactions, the HCl reacts rapidly with the calcite, dissolving the calcium carbonates and forming soluble calcium chloride with CO2 and water. So the HCl reacts very well with calcite dissolutions, and also reacts very good with dolomite. So dissolving it into calcium chloride and magnesium chloride, which are soluble in water, as you may know. So that's why HCl working very good with carbonates and creating, as you see here in this picture, creating what is so-called the wormholes. So instead of attacking the damage that you may have even during drilling, whatever, it reacts with the composition, with the rock itself, and creating these wormholes, and it can easily bypass the damage and goes and open access to the reservoir. So yeah, so this is the mechanism of HCl. Can penetrate deep into the formation by creating what's so known as a wormholes, by passing nearby well damage and significantly increasing the permeability. And the acid, flows into the reservoir and reacts with the most permeable pathways effectively, and propagating these wormholes further into the formation. The other thing is the reaction between HCl and carbonate minerals are typically are rapid, often requiring careful control to ensure that the acid does not spin too quickly, so we don't spend all the acid too quickly. So this is we will have less penetration into the reservoir, and may lead to uneven treatment or insufficient penetration. So what is the main challenge in the when it comes to matrix acidizing in carbonate? The first one is the acid spending. So the high reactivity of HCl, of hydrochloric acid, with the carbonate, minerals can cause the acid to spin too quickly near the well pore, and this is limiting its effectiveness into penetration penetrating, into the reservoir. So as an overcome, or how to overcome this challenge, is by adding acid retarders, or staged treatments are sometimes used to control the reaction rates. The other thing is the wormhole control. Okay, we are happy that these are wormholes being created to bypass damage, but in some cases you have no control where the direction or how these wormholes are being propagated. So to prevent, we need to control to prevent this extensive acid loss into the formation, and ensure that the treatment reaches the desired depth. So that's why if you have a little bit high water cut in carbonates with matrix acidizing, sometimes these wormholes connect the well with the water production, and you end up with a very high water production in carbonate. So that's why you need to control the volumes and the injection pressure. All these are parameters that controls the propagation of the wormholes. So as a conclusion for matrix acidizing, in sandstone, matrix acidizing focus on dissolving silicate minerals and clay using hydrofluoric acid with the help of hydrochloric acid. So primarily aimed to unblock the pores and stabilizing the fines. So the process requires careful management to prevent secondary precipitations and to address the clay sensitivities. In carbonate formations, matrix acidizing using only hydrochloric acid to dissolve the carbonate minerals, creating wormholes that enhance permeability. And the process is more straightforward, but requires careful to control to manage actually the rapid reactions rates and ensure the penetration as well. Moving to the last but not the least type of acid, which is the fracture acidizing. The fracture acidizing treatments have been, generally confined to carbonate formations, including, all type of carbonate formations, either vagular or natural fractured chalks, limestone, and dolomite. All these, are good candidates for acid frac. So the acid frac treatments of carbonates are conducted to serve two main objectives. As you see here, the first one bypassing formation damage, and the other one stimulating undamaged formation. So this is the advantage. This is the advantage of acid frac, is to not only bypass the damage as it could be done by matrix acidizing, but also stimulating the undamaged formation. So we go deep into the formation. So this is the advantage of acid fracturing. So it's actually it could be as an alternative of to matrix acidizing, as well as that the matrix acidizing is not enough. Sometimes the formation damage is really deep. So the objectives of fracturing, applications are, the same more or less. The creating long, open, conductive channeling into the reservoir, so extending deeper into the formation. This cannot be achieved throughout the matrix stimulation. The basic principles of fracture propagation and the geometry are also, the same in terms of wormholes, because we're talking about carbonates. The difference between, the two fracturing methods, is how the fracture conductivity is created and, maintained. This is, considering the hydraulic fracturing, is maintained by, propagating an open fraction created with a solid material such as, sand or, certain lighter materials. So when we use, hydraulic fracturing, these materials are referred to as propant. We don't use, in hydraulic fracturing, we use propant. But in fracture acidizing, acid is injected into the fracture created by, a viscous fluid, or this viscous fluid is being used to create, this fracture by injecting it in a very high pressure. So the acid travels down to the fracture and transported to the fracture walls, resulting in dissolving, dissolution and performing the etching phenomena into the rock itself. So if the etching is non-uniform, it's like differential. Again, it's the whole formation. Then the fracture may close within, reduce the conductivity. So that's why one of the most important parameters that we need to consider in acid frac is the making sure the uniformity of the etching to cover the to cover the longest, depth into the reservoir. So as you can see here in this figure that shows, the two halves of long core that has been, open to show the rock surface dissolution, and this resulting from an experiment, simulating fracture acidizing. So here we have the last slide. I would like to give you some points that to take it with you when it comes to formation damage. So formation damage refers to the impairment of reservoir ability to produce hydrocarbons due to physical or chemical alterations in the rock and fluids, often resulting from drilling, completion, or production additives or production activities, preventing, after having or before, before having this formation damage, we might think of preventing formation damage throughout, optimizing drilling practices, effective completion design, and careful production management is really crucial to maintain the well performance. And when the damage occurs, so you need to diagnose this case. So there are diagnostic tools like pressure transient analysis and well testing that will help you identify the extent and the severity of the formation damage. And after diagnosing, then you will propose the best efficient way. There are many mitigation techniques such as matrix acidizing and hydraulic fracturing are the or acid frac are employed to restore or enhance the permeability, in the formations. So I would say that continuous monitoring and with a very cost effective way to ensure that the chosen stimulation methods are very effective and economically viable. This is for sure. So this will maximize the hydrocarbon recovery and the well productivity. Thank you all for being patient.